It's a pleasure to introduce my colleague Jim Phil, our colleague Jim Phil. A little bit about Jim and putting it in the context of me.
Okay.
So he was born 6 months after me in Illinois. I was not born in Illinois. He attended University of Illinois 5 years before I did. Got his master's degree the same year I did. Received his PhD 2 years before I did. Came to Johns Hopkins 6 years after I did. And actually, the most interesting thing is the theorem that he's going to tell us about. One of the theorems he's going to tell us about today, he got before I ever would have proved. So, got a proof of before I ever would have gotten it. So, Jim, without further.
But it's a theorem of Dan Naiman's. Okay. So, the work I'm going to be discussing today is joint with Dan Naiman. And, but any errors that appear in the slides are totally on me, except somehow, inexplicably, I'll blame them on Carrie Breed. Mainly because his stick is sitting up here safely against the wall.
Stick is recording.
All right. So I'm going to start this seminar the same way that Dan started his seminar last year. And in fact, that's how I became interested in this topic, by attending the seminar. And then Dan and I figured out some questions that he had asked last year. So the purpose of starting with the example I'm going to start with is to give a sort of gentle, friendly introduction to the notion of multivariate records. Before I do that, it might be a good idea to review what's meant by univariate records. All right, so the example here is the world's men's best long jumps by calendar year. All right, and for the purposes of this data set, I'm going to take year 0 to be 1960. So there it was, something like 8.2 meters. Okay. The next year, a record was broken. We'd all agree, right? And the following year. Next year, not so much, right? No record in 1963, because the value in 1963 is dominated by the value in 1962, and also by 1961, right? Okay, and so there were some years where records were set and others where records weren't set, and everybody was sort of jumping around 8.25 meters, and then in 1968 at the Mexico Olympics, yes, Bob Beamon shattered the record. All right, so for a long time after that, no records, until it was either 1990 or 91, I forget. Mike Powell, I think that was in Tokyo, right? But not at an Olympics, as I recall. Anyway, he set the record, and that remains the record to this day. Okay. So in this data set, there are, the records are shown in red. There are 8 records that were set in the first 60 years of this. Each time that a new record is set, precisely one record is broken. I'm discounting the possibility of ties. In the model that I use later on, there won't be any ties, so let's sweep that under the rug. Okay, so anyway, that's univariate records, right? What do I mean by multivariate records? In particular, what do we mean by bivariate records? Well, let's look now at both the men's and women's best long jumps by year. And I'm plotting not versus time, but I'm plotting women's on the horizontal axis and men's on the vertical axis. So there's 1960. By default, it sets a bivariate record. And let me explain the red lines that you're going to see drawn and moving in this next series of pictures. The region to the right and above the red boundary indicates the record-setting region. That is where a point would have to land in order to be considered a bivariate record according to the definition that we're going to use. And I'll explain that definition as we go. Certainly, I think anyone would say in 1961, a bivariate record was set because a univariate record was set both for women's and for men's, right? So that shifts the record-setting boundary, the frontier of records to there. Similarly, in 1962. 1963, I think we'd all agree, was not by any sensible definition of record because it's dominated in both the horizontal and vertical coordinates. 1964, a bivariate record. Here's the first case it gets interesting. We'll say that 1965 also sets a bivariate record because this point for 1965 is not dominated in both coordinates. coordinates by any previously occurring point. Okay? It is dominated in the x coordinate, but not in the y coordinate. So we'll say that 1965 sets a bivariate record, but it doesn't break the 1964 record. 1964's observation still has the property that it is not dominated in both coordinates by any record, any observation that's occurred up until now. Okay, but that requires us to adjust the boundary like this. There's a little indentation there, a little staircase behavior. If an observation were to fall right in here, it would set a bivariate record. Okay, 1966 is not a record. I skipped 2 years ahead here. 1967 sets a record. Well, there's a tie, but I'll consider it setting a record, but it doesn't break any, and so on. I think you're getting the idea. Let me advance the picture. Okay. So here we go. And now, after 1991, so I guess it was 91 when Powell set the record, and then after that, no records have been set. Okay, so that's the current, the picture as of 2018. All right, is everybody clear on that? Okay. I've now gone through something like 130 of my slides, and there's only about 30 left. So what am I going to do in this talk? I'm going to discuss some very basic results about a very basic model for multivariate records. It surprised me, certainly, that these questions had not been considered previously. Okay? So the very simple model, which you might use as a null hypothesis type model in a statistical investigation, is this. We're going to collect observations sequentially. I'll call them x super 1, x super 2, and so on, because I'm going to reserve subscripts for the coordinates of these multivariate observations. We're going to assume that these multivariate observations are i.i.d, and we're going to assume within each observation that the coordinates are i.i.d. For what I'm going to say, it's important that the coordinates be independent. It's not important that they be identically distributed, but that will be convenient to assume. Okay? Furthermore, I should mention that as far as I know, almost nothing, including not even anything like the basic results I'm going to talk about today, have been done in other situations where you assume some sort of, for example, a Markov model on the observations, or positive or negative correlations among the coordinates. Okay? So that's our very simple model, and we're going to see how do multivariate records behave under that null model. All right. In terms of counting records, it's pretty clear that it doesn't matter what distribution you assume for each of the coordinates, as long as you take it to be continuous. All right? So for practical purposes, it's going to be convenient to take the distribution to be either uniform on 0, 1 or exponential with mean 1. Okay? And I'll try to be clear when it matters which sort of assumption I'm making. All right, so Dan and I wrote 2 papers together. I wrote a paper by myself. These 3 papers are all available on the archive. They were all submitted in January to respectable publications. We haven't heard yet on any of the 3 papers, so maybe it's time to ping them. Rather than referring to them as something like A, B, and C, I'm going to refer to them with letters that I hope will help you remember which is which. I'm going to address the following 3 questions, primarily the second, but I'll have some things to say about all 3. First question is, how can you sample, or generate, that's what the G is, how can you sample multivariate records efficiently? Second question is, how does the record setting frontier, the red boundary that we saw in the long jump pictures, how does that behave asymptotically as the number of observations becomes large? And third, what can we say about the number of records that are broken when a new record is set? We saw in the examples that sometimes no records are broken when a record is set. Sometimes all the previous records are broken, and it can be anywhere in between, right? So what can we say about the distribution of the number of records broken? All right, those are the questions I'm going to consider.
It's interesting, Jim, but what is the connection with quicksort?
Yes. To my knowledge, no connection with quicksort in this talk. No gasps. I thought that. Gasps. Okay. So, all right. This page is pretty much all of the notation and terminology you'll need to know for the talk, and I hope it's pretty understandable. I'll write x sub plus for the sum of coordinates of a vector x1 through xd. There will be slightly different notation for, precedes in LaTeX and less than or equal to, corresponding to ordering of coordinates. For the first time listening to this talk, unfortunately for most of you, this is you'll only have to go through this once.
And back to quicksort.
Pardon me? Yeah. The distinction between this symbol and this symbol can be ignored, right, pretty safely. It actually, even though there are no ties by the model we're assuming, with probability 1 there are no ties, there is a small need for the distinction between these two, but you don't have to pay too much attention to that. All right, so now the next three just put into words what you saw in the pictures, right? We'll say that the kth observation is a record, or a multivariate record, or a Pareto record, or that it sets a record at time k, if it's not dominated by any of the previous observations. Okay? We'll say that the kth observation is a current record, or a remaining record, or a maximum at time n, if it has the property that it hasn't been dominated by time n. Okay? Yes?
So when it sets a Pareto record, you're not actually necessarily logging which coordinate was the source of the record.
That's right.
Okay,
That's right.
so it just sets a record if it's bigger in one coordinate.
If it fails to be dominated in at least, if in at least one coordinate it fails to be dominated, then it's a record.
Which doesn't mean it has to be bigger in any coordinate.
That's right. Yeah. It doesn't have to be setting a univariate record in any one of the coordinates. Okay, and we'll say that the kth observation is a broken record at time n. If it's a record, that is when it occurred, it wasn't dominated, but it's not a current record. Okay, that is if it wasn't dominated previously, but it has been dominated since then. And the first time at which the record becomes no longer a current record, we'll say that the record is broken at that time, okay, by the observation at that time. We invented all this terminology. We just tried to make it like ordinary usage for univariate case, setting records, breaking records. In the univariate case, setting a record and breaking a record in the absence of ties is exactly the same thing, right? But in the multivariate setting, it's not the same. All right, I will have just occasional use for this notation. Capital Rn is going to be the number of records that were set by time n, whether or not they've been broken since they were set. Little rn is going to denote the number of remaining records at time n, and beta for broken is going to represent the number of broken records at time n. So that's just capital Rn minus little rn. Okay, of course, the number of records can only go up, the number of broken records can only go up, but the number of remaining records can fluctuate, as we saw in the example, right? Okay. Little fact about the connection between remaining records and broken records in distribution. That was covered by Dan last year in his talk. I don't really need that fact, so I'll skip over that now. Okay, so the record-setting region is just at time n, it's just the set of points where it's just the region where if a point were to fall into that region at time n plus 1, it would set a record, right? I'll show you a picture here, right? So suppose it's now time n. There are 10 current records indicated by red, or for Vittorio, it's like red or green. It's not necessarily time 10. There could be lots of observations that either weren't records or are now broken records at this time, right? But the current records are shown in red. And the record-setting region is the set of points to the right and above this staircase boundary, right? The staircase boundary is what we'll call the frontier, the record-setting frontier.
And is that actually just a Pareto Frontier?
Yeah, so the terminology Pareto Frontier is used rather loosely, where it's not clear whether it's meant to refer to the set of current records or the boundary or what. We had originally decided to call this staircase curve a boundary, but then it turns out that for the probabilistic techniques we use, we made use of boundary crossing probabilities, and we didn't want to have the two uses of boundary. So we chose frontier, and then I found out people call it the Pareto Frontier. So anyway, for us it's a technical term. We'll call the topological boundary of the record-setting region relative to the closed positive orth and determined by the origin. I guess there I'm assuming either some non-negative random variable in the coordinates like uniform or exponential. We'll call that the frontier. All right? So the terminology for record-setting region is natural, since an observation falls into the record-setting region if and only if it sets a record. So there's the picture. But here's what we're going to be interested in. When you stand back from this picture or sit in the back row of the classroom and don't have your glasses on, it might be that this staircase function looks pretty close to linear. In fact, let me show you a picture with after 10,000 records. Now I think we'd all say, yeah, there's not too much deviation from linearity in this case, right? So we'll have a theorem that says, yeah, the points are roughly linear in 2 dimensions or hyperplanar in dimension D, right? And we'll be interested in how much deviation there is from this linearity, right? And the way we'll measure that is by saying, so we'll try to figure out what's the approximate sum of coordinates for any point along this frontier. But we'll ask the questions, what is the largest sum of coordinates? In this picture, it corresponds to this current record, right? We'll call the largest sum of coordinates, so we'll call the frontier f sub n, after n observations are collected. We'll call the largest sum of coordinates f plus sub n, and we'll call the smallest sum of coordinates, which in this case corresponds to this point, we'll call that f minus sub n, right? So we'll be interested in where is this frontier located and how wide is it, and we'll measure that somewhat crudely by saying, what's the difference between fn plus and fn minus?
What's the slope of the line?
Yeah, that's what we're going to be interested in. Where is the line located? Where is an approximating line or hyperplane in general, and then how much deviation is there from it in the worst case, plus and minus. Okay? Yeah, so we'll get to that. All right, but not yet. First question I want to address is, how can we sample multivariate records efficiently? So Dan and I have sampled multivariate records efficiently, and I'm going to explain that in a minute, but first I want to show you this picture. This is the picture that results after 10,000 records were generated using a certain sampling algorithm that I'm going to explain. Okay? There aren't 10,000 points along this boundary. Again, remember that means there were 10,000 records generated, some of which have been broken. I think there's something like 200 or so, I forget, 200 or so current records. Okay, so the question is, how did we get this figure? And here's a spoiler. We didn't do it by generating bivariate observations. So first of all, sorry, I should mention, it's very important for this segment of the talk that we're talking about exponentially distributed coordinates, right? If you had uniformly distributed coordinates, you'd still be able to see a pattern, but the picture would be distorted. I think Don asked a question last year about that during Dan's talk. Yeah, so it's important here that we're using exponential coordinates. All right, so spoiler, we didn't do it by generating observations and waiting for 10,000 records to be generated.
Which is called the carry method.
Why didn't we do that? Because we'd still be doing it, and we'd be doing it next year and while we're dead and so on, right? Because here's a result from our paper, a weaker version than what we have in the paper. Suppose, let's let t sub n denote the time it takes to get m records, the time in terms of number of observations. Then with capital L throughout this talk denoting natural logarithm, the log of tm divided by d factorial m raised to the 1 over d power converges almost surely to 1. So, as in the figure, when d is 2 and m equals 10,000, that gives you that t sub 10,000 is about 10 to the 61st power. So we would have had to generate 10 to the 61st observations to get 10,000 records. That's not how we did it, okay? So how did we do it? Well, now let me shift to say, let's suppose that the coordinates are distributed uniform. That'll make the treatment here a little bit easier to present. course, you can shift back and forth between uniform and exponential if you want, right? All right, then we saw in the picture 3 slides back, and I'll show you a 3-dimensional picture in a second, that the record-setting region is a non-disjoint union of translated positive orthants. What am I talking about? Well, the record-setting region, remember, in this 2-dimensional case, was all the points above and to the right of the staircase function. That is the non-disjoint union of this translated positive orthant and this translated positive orthant and this one, and so on, okay? And now the question is, how do you, oh, so let me show you a 3-dimensional picture too. Now, Vittorio, you're really in trouble here because I'm using colors all over the place. So let me explain that. For people who don't know, Vittorio was saying before the talk he's colorblind, and so red and green in particular are the same, right? Sorry about that, but okay. So this is a 3-dimensional picture. As in the previous picture, the remaining records are shown in red. That's these points, right? But the record-setting region at this time is a union of 17 translated orthants. And the 17 vertices, if you might call them, or origins of these translated orthants are what we call generators, okay? And the 17 generators are shown in purple, blue, and green. The purple ones, there's an example here, right? Another one here, and another one here. So you should think of like, the record-setting region is coming out from the screen, right? The purple ones are one-dimensional generators in the sense that 2 of their coordinates are 0. The blue ones are 2-dimensional coordinates, and the green ones are 3-dimensional coordinates, okay? So there's an example of a 3-dimensional coordinate, and the orthant is the one shown by the dotted lines here, right, coming out of the screen towards you, okay? So, all right, so we want to know how can we sample from the record-setting region represented as the union of translated positive orthants. And Dan explained this in the seminar last year. It's very simple, right? You just sample a generator from the set of generators proportional to the volume of the corresponding orthants. Remember, I'm using uniform coordinates now, so it's, the probability content is just the area of the orthant, right, or the volume of the orthant. Okay, so you do that. Of course.
Now they're boxes, because you're in the uniform case.
Yeah.
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 The orthants
Oh,
are
not
boxes.
orthants. That's right.
Orthants are boxes.
That's right. Right. Boxes. Right. There's the upper bound limit on right. Exactly. Yeah. Thanks. Very good. Thanks. Okay. So boxes. Right. But there will be some points in the record-setting region that are in multiple boxes. Right? Like, for example, a point like this, for sure, is in a lot of the boxes, right? And so just doing the first 2 steps here, sampling proportional to the volume, and then sampling from the orthant, oversamples the points that are in lots of orthants and undersamples the ones that are only a few. Of course, it's easy to adjust. All you have to do is accept the sampled observation as a new record with probability equal to the reciprocal of the number of generator boxes to which it belongs, okay? And if that fails, you just repeat the steps. And that's easy. Okay, but then, of course, when you generated a new record, now you have to update the set of generators. And that's not so simple. It's not terrifically difficult, but it's not so simple. And analyzing how many generators there are at various times is interesting and non-trivial, but that's described in our generators paper. Okay. So a couple of remarks. Results are easier to discover empirically in records time, but easier to prove in observations time because of the i.i.d. Property of the observations. And results in observations time can be transferred to results in records time using time change arguments or switching relation arguments that exploit information concerning how the counts of number of records grow with n, or equivalently how the time of the nth record grows with the index count. Okay, so that's discussed in detail in sections 4 to 5 of our Frontier paper. Okay. From now on in the talk, I'm going to take the observations, the observation coordinates to be distributed exponential with a mean Okay, so you remember we saw this nearly linear figure for dimension 2 after 10,000 records were generated. So the next questions I'm going to consider, these are discussed in the Frontier paper, is where is the frontier located? Okay. What is an approximating hyperplane? And how thick, that is how wide, is the frontier? And I'm going to be moderately precise. They're sharper answers, but still not completely sharp answers given in our Frontiers paper. Okay, so the first question, where is the frontier located? That's actually pretty easy to answer. And I'll summarize it this way. The deviations of the sum of coordinates for a generic current record, a generic red point in my picture, at time n, from the value natural log of n, are typically of constant order. And I have a more precise result down here that I'll get to in a second, okay? So to formulate that mathematically, I have to decide, well, what do we mean by a generic current record? Okay, and so, well, I mean, you want to take an observation and condition on it being a current record. But of course, there have been, by time n observations, right? So pick one, observation k, and ask about the conditional distribution of its sum of coordinates given that it's a current record at time n. Doesn't take long to convince yourself that that doesn't depend on the value k, and so in particular it's the value when k, it's the distribution when k equals n, so it's just the conditional distribution of x plus super n, given that x super n is a current record at time n, that is given that x super n sets a record. Okay, so the distribution that I'm talking about just depends on n, not on the which record, which observation k we're talking about. So let's denote a random variable with that distribution by y sub n. And I'm asking, what's the distribution of yn? And the answer is, if you take yn and subtract natural log of n, you get convergence in distribution to a standard Gumbel random variable, standard double exponential extremal distribution. Advertisement for the 553.720/721 course, one of the examples that will appear in the course is the Gumbel distribution, and one of the theorems that will appear in that course is a theorem that I'm going to mention is used to prove the result, namely Chaffee's theorem. Okay, and I won't go through the details, but here's how the proof goes. You can figure out exactly what the density is for this random variable, y sub n minus log n. And then by a very simple, and here it is, okay, that's the density, and the value p sub n is the probability, I wrote it over here, is the probability that the nth observation sets a record. And there's an asymptotic expression known for that, well known for a long time, right? Okay, so what you find out is that the density for yn converges pointwise to the standard Gumbel density, which is e to the minus y times e to the minus y, right? And so Chaffee's theorem says, therefore, that you have not just convergence in distribution, but in fact a stronger form of convergence called convergence in total variation, or strong convergence it's sometimes called. All right? So don't get lost in the technicalities. The idea is that the sum of the coordinates is about log n, and typically along the frontier, and typically only differing, or at least for the, I should say, not necessarily along the frontier, but at least for the current records, right? That the red points on the frontier, it's about log n, and the typical deviations from that are only on the order of a constant. All right, but there are lots of current records at time n, right? And so the typical deviations might not be of the same size as the largest deviations, right? So the question is, how much does Fn plus differ from log n, and how much does Fn minus differ from log n? So a reminder that Fn plus is the biggest sum of coordinates. In this picture, that corresponds to that current record, and Fn minus is the smallest sum of coordinates. In this case, that corresponds to a generator, this particular generator, right? And we define the width, Wn, to be the difference between Fn plus and Fn minus. All right, so how do Fn plus and Fn minus behave? Here's a very rough statement of the main results. I will use L sub k to denote the kth iterate of natural logarithm. Okay? Unlike for the generic sum of coordinates, yn, that I talked about just a second ago, deviations of fn plus from log n are exactly of order log n. I'll make that more precise coming up, but that's one of the takeaway points, right? Whereas deviations of fn minus from log n are of smaller order than log n. This is fortunate. Studying fn plus and fn minus bivariately would be difficult. We only have, because of the difference in orders of magnitude here, we only have to study fn plus and fn minus separately in order to study wn. But you might say, okay, but what are these deviations? What order do they have? In one direction, we can show log n, and Svante Jansson conjectures, I'll have it on a later slide, that that's the right order, that is deviations of fn minus from log n are of exactly of order log n, typically, yes.
So typically when you get bounds like this, one of them you can acquire without necessarily an independence assumption, and the other one, there's an independence assumption that's critical for, like, you know, a Borel-Cantelli or whatever. So do you have either one of these that holds when you drop the dependence assumption?
All the students who haven't started dissertation work yet, that's a terrific question. We don't know about that. The techniques that we use very heavily rely on independence between the coordinates and independence between the observations.
For both bounds?
Yeah.
So you can't preserve
Right.
either of them without?
Right.
Okay.
Well,
Right.
you might be able to, but you haven't.
No, I mean, we haven't done that. What I'm saying is we haven't investigated that at all.
Whatever you're doing, like, it's not Borel-Cantelli 2 for one bound and the other bound you can do without.
We do use Borel-Cantelli lemma up the wazoo, as you'll see in a moment. A lot. Actually, we use results of Jack Kiefer, who used lots and lots of Borel-Cantelli arguments. So we haven't thought about what happens if you get rid of the independence assumptions. That would make a terrific dissertation investigation. I guess I should be fashionable. A dissertation inquiry, how's that? But my impression is that it would really complicate things. You know, is that you really, the independence we're using in a way that greatly simplifies everything. Both parts.
Jim, do you have time and/or inclination to give a one-sentence intuition for why f minus is smaller order than f plus?
Yeah, I have more than that. I have a few slides about that. First of all, let's take care of fn plus, because that's really easy and classical. And the key is this lemma, which characterizes fn plus. As you would have guessed from the pictures that you've seen, fn plus is not just the largest sum of coordinates anywhere along the frontier. It's also, more specifically, the largest sum of coordinates of any observation up through time n, right? In the picture, it was clear that that fn plus would be achieved by one of the red points, right? Because the stairs stick out in that direction, right? That's clear intuitively.